Now that we have a way to track the concentrations, we can use that to calculate the overall voltage using the Nernst equation. So these are the half reactions that we know that we have, and then this is the Nernst equation. So the Nernst equation gives us the voltage at non-standard conditions, and it's the standard redox potential plus RT over NF times natural log of the reaction quotient. So for our overall battery voltage, what we want is the positive voltage, which we calculate based on the Nernst equation. So we'll use this term will be equal to the positive standard redox potential, which is equal to 1.01, and then plus this term for our positive reaction on our positive half cell. And then this term will be equal to our negative standard redox potential, which is negative 0.25, plus this term for the negative half cell reaction. And then plus any overpotentials that we have. So that would be like resistance and kinetics losses. But for this, we're going to ignore those overpotentials and just look at, based on the Nernst equation, what's the overall voltage. So this is the full Nernst equation for this battery with all the concentrations here. So we can see as we discharge the battery, we have less protons and less vanadium dioxide, which are in the numerator here. So this fraction will decrease in overall size and become smaller. And then we have greater amounts of vanadium oxide, which is on the denominator. So again, as we discharge it, this fraction will become smaller. And natural log of a fraction is gets increasingly more negative as the fraction gets closer to zero. So this term becomes increasingly negative as our concentrations, as we discharge the battery and we have less of these concentrations and more of these concentrations. So we see the same thing if we look at the concentrations in the negative cell. When we discharge it, we have less of the vanadium 2+, which is in the numerator, so decreasing the size of the fraction. And we have more of the vanadium 3+, so which is in the denominator, so again, decreases the overall size of the fraction. So what we want to do is figure out exactly what these concentrations are. And since we know what these are, we can just plug in each of these concentrations at each point in time and then figure out the overall voltage. So if we look at the code that we already have, what did we run here? So we also have these diffusion coefficients that we can plug in for each of our different species. So we're going to need to simulate each of these species. So the one that we have here is that we already did is a 4.54. So that's going to be our vanadium oxide. So if we look at our vanadium oxide, that's going to be a product. As we discharge, we're going to increase the amount of vanadium oxide. So let's see. I think we want our current to be negative so that we increase the amount of vanadium oxide over time. Yeah. So you're going to want to run this with a negative current for the vanadium oxide. And I'm going to set the name of this concentrations output that gives us all the concentrations. I'm going to set it to concentrations underscore vanadium oxide, just VO, so that I know which concentrations of which species we're looking at there. So now we just want to run this again, but for which species? We can do vanadium dioxide next. So vanadium dioxide, as we run our battery, we're going to have less of vanadium dioxide and it's going to be at the same rate as we're increasing the amount of vanadium oxide. So we just want to switch the sign of this current so that we simulate the behavior as it is decreasing in concentration at that electrode. So, and then I'm also going to change this name of the concentration to VO2, since that's what we're tracking here. And then we also want to look at what are the initial concentrations here. So if we're discharging the battery, we obviously want to have more of these reactants at the start. So I'm going to say, I found this paper that has some examples for concentrations, and they said that the total concentration of vanadium in both the positive and the negative half cells is 1,500 moles per meter cubed. So I'm gonna set the initial concentration of my vanadium dioxide to be 1,500, and I'm gonna set my initial concentration of the vanadium oxide to be 0. So that way we have a total amount of vanadium as 1,500 moles per meter cubed. And we're basically saying it's 100% state of charge here. So yes, and then we also need to change this diffusion coefficient for the vanadium dioxide. So that's going to be 3.82 times 10 to the negative 10th for this diffusion coefficient. And then is anything else? All of these other parameters should be fine, I'm pretty sure. Yeah. So now we want to look at the concentrations in the negative electrolyte. So we have V2 plus, that is going to be our reactant. So again, I'm just going to run this. I'm going to change the name of the output. I'm going to make it just V2. And then the initial concentration, again, this is a reactant, so we want to have more of it at the start. And since both the negative and positive electrode have an overall concentration of vanadium of 1,500, this one is going to be 1,500. And then we want to change the diffusion coefficient for V2 is going to be 1.05 times 10 to the negative 10th. So now that should be good. And then the last one that we need here is the V3. So that's a product here. So I'm going to start with a concentration of 0 and then change the diffusion coefficient to 2.54 times 10 to the negative 10th. And then, so for these currents here, the concentration of V3 should be increasing and the concentration of V2 should be decreasing. So we want a negative current on our V3 and a positive current on our V2. So that'll decrease the amount of V2 at the surface where it's reacting, and it'll increase the amount of V3 at that surface where that reaction is happening. So these should give us all of the concentrations throughout the battery at every point in time when we want to track them. So now what we need to do is figure out how do we implement this equation with these values that we get. So all of these concentrations are in this equation, they're at the surface where the reaction is happening, which in our case is the electrode. So like when we run this, the place where the reaction is happening is along like this surface, right? It's our like left boundary here. This is where the reaction is happening. And this is where we want to find the concentrations. So the concentrations we're looking for are going to be like initially we'll have this point, and then further in time, we want to be looking at something like this point. Basically, we're just tracking this edge of the concentrations. So we set up what our overall Nernst equation is here. So E equals, first we need these standard redox potentials. So we get those from over here. It's going to be 1.01 minus a negative 0.25, so plus 0.25. So we have 1.01 plus 0.25. And then we need our RT over NF. And we're gonna need to define R and T. R is, what is it again? It's like 8 point something. I'm just gonna copy and paste these. So our R is 8.314, and our temperature is like approximately room temperature, 298 kelvins, somewhere around there. So then what else do we need? N represents the number of electrons that's transferred in either of these reactions. So that's 1 in both of these reactions. 1 electron is transferred. So you can put that in. N equals 1. Now I want to set up our equation here. So we have R times T over N times F. And then we want to multiply it by our natural log of, first we have the concentration of vanadium dioxide at the surface. So that is going to be the concentrations of vanadium dioxide. And we specifically want it at the surface.
Hey, Maya, Balkan said if you can let him in.
Oh, whoops, yeah. I gotta stop screen sharing. Okay, so let's see. Yeah, so we're looking at we're putting in the concentrations of vanadium dioxide, and this is going to be at the surface. So we want a vector of the concentration at the surface at each point in time. So let's see, the way that we made this concentrations matrix, we have along one side we have space, and on this side we have time. So we want, I think we want to specify the first row. We want all of the first row. So that'll be this indice. And then we multiply this by our vanadium 2+ concentration of vanadium 2. And again, it's going to be at, we want this first row of data. And then we also are going to need this H+, the proton concentrations, but we'll do that after we set this up. So that's on the numerator, and then in the denominator we have our vanadium oxide. So concentrations of vanadium oxide. Again, we want the first row of data. And this is multiplied by the concentrations of vanadium 3+ at that first row. So now we have this. What we need to do now is figure out what are our concentrations of protons. And so the protons have a much higher diffusion coefficient than the other species here, like the vanadium species, because the protons are much smaller. So we're gonna assume that there is almost no concentration gradient here. So like where with the vanadium species, we see this change buildup, we're gonna assume that in the hydrogen, the diffusion coefficient is so high that essentially we just see the same concentration everywhere, even when it changes, just because it can diffuse and create a level concentration gradient at every point in time because the diffusion coefficient is so high. So we're just going to figure out what is the rate over time at which the hydrogen ions are being transferred from one one side of the electrolyte, from the positive electrolyte to the negative electrolyte, or vice versa. We just want to see overall what is that amount of reaction that's happening. So we can use Faraday's law to figure out what this number should be. So that's going to end up being, let me share my iPad screen. Sorry, give me a second. My iPad is not working with me. Okay. So Faraday's law of electrolysis gives us that the total mass transferred or deposited is equal to the charge times the molecular weight of the species over Faraday's constant times Z. So what we want is, what is the change of concentration over some time? So to get that, and we want it in terms of current. So what we can do is say, we can divide this over the molecular weight. So that'll give us mass over molecular weight is just the number of moles. And then the total charge is equal to current times time. So you can replace that. And then it's over Faraday's constant times Z. And so we want concentration, so we want moles per some volume. So I'm just going to divide both sides by volume. So now we have some concentration. This is concentration over some time equals just this. So if we want to figure out what's the change in concentration at some time, we can multiply this back over. So this is the amount per some change in time that we want to see how much hydrogen is being transferred from one side to the other in our system. So I'm going to share my Matlab again, and then so we want to make a new function to just track our hydrogen here. So this function We just need concentrations. We can take these same parameters from our previous function. So from this, we're going to want a concentration matrix, which is going to have, since we're just looking at it at one point in space, we're not tracking throughout space, we're assuming it's all the same. We just need a vector that is a row vector, basically, that has a dimension of nt, which we're also going to need to define here. It's defined the same as we have it previously. So nt is the total number of intervals through time that we need. So that's going to be time over delta t, or the time step that we have. So that's going to be the total number of time steps that we use. So let's also define our nt in this function. So now we have our concentrations. Now we want to make a for loop that iterates through each step in time and figures out what the concentration of the protons is going to be. So for some, we want this to go for nt number of steps, since that's the number of iterations through time. So for t equals 1 through nt, we want first we want to define concentrations. We want to define what our concentrations are. So at our first time step, this is going to be, actually, let's define, before we start this for loop, the initial concentration, which is going to be our initial whatever we input. So we have some initial concentration that we start with, and then we want to increase it by the amount delta t times current over Faraday's constant times z times volume. So concentrations at there's a new concentration equals the concentration at t minus 1 plus the change in concentration. So that's going to be dt times current over Faraday's constant. Z is 1, so I'm just not going to put it in. Volume is area times, I think it should be length. And then our new concentration at this time is equal to new concentration. I guess you could just set this here. Will this work? So at each new time step, we'll say, based on the previous concentration, we can figure out what the new concentration is going to be, and then we'll set that into our matrix. It sounds like it'll work. All right, so this is our function for the hydrogen. So now we want to run that as well. So concentrations of protons equals, let's name it something different, solver protons So our initial concentration, let's see, what did this paper say? So they said, and again, we're tracking the protons in the positive side of the battery specifically. So proton concentration at state of charge equals 0, 6,000. Yeah, sure, we'll just plug that in. So it'll be, our initial concentration will be 6,000 moles per meter cubed. Our diffusion coefficient is actually irrelevant. We don't really need this parameter. Our current, we want it to be the same as this. And it should, we should be, since it's a reactant, we want to be decreasing the amount of protons in the positive half cell. So I'm going to make this current negative, just based on this equation. So if we have a negative, we're going to decrease the amount of concentration. Our area, we can make it the same as before. So this is, the length will be 1 millimeter. And the step through time is also not relevant. The amount of time, 30 seconds, and then the step through time, the 0.01. So now that we have this should give us the concentration of protons at each step in time, and it should be approximately equal to the concentration at the reaction site, since we're assuming that it'll be able to diffuse so quickly that there's almost no concentration gradient at any time. So now we want to put this into our overall equation. So that'll give us, it'll be in the numerator here, and I forgot something. in this equation, since each time this reaction happens, you're gonna lose two moles of protons for every 1 mole of vanadium dioxide. I'm gonna multiply this by 2, since this is the amount that it changes each time, and it's based on the moles of current that we have. And since for each 1 mole of electrons, we're losing 2 moles of protons, we want this to be multiplied by 2. So yes, so we want to add in this proton term to our overall Nernst equation. So I'm going to put it concentrations of H. And this one, since it's already a row vector at each point in time, we don't need to specify an indice, but we do want to square it, since since it is 2 moles, we square it in the reaction quotient. So we're going to square it, and since it's a vector, you need to put this dot exponent. And actually, for this division, I think you also need to put a dot before it, and for all of these, for all of the multiplication as well. So put just dots before every operator. Log should be fine, I think, and these operations should be fine. All right, and then let's see, we want to plot our, for our time, we can use our t-axis from before. And then for our y, we can just make it e. Well, let's see if this works. Okay, error in 1, 164.
I think that error is because you're doing t minus 1 initially, so that gets you 0, and you can't have zeros.
Yeah, let's try it with, just change it to 2. See if that works. Suppress all of these too. Okay. Oh, you gotta give it Faraday's constant within the function. Should have the rest of these things. Okay, so, all right, so this is just a concentration gradient. We had that before, and oh, it overwrote the other figure. Okay, let me run that again, but try and make it a separate figure. Okay, so here we have the voltages over time. So we see past here, basically, this is no longer, the battery would be dead. All of this is like this doesn't represent any like physical battery properties. It's basically this this curve represents the voltage of the battery over time. So it's pretty much what we would expect. Starts at a reasonable voltage, and so it dies within like 3 seconds. Is that right? Yeah, I guess it does. So we can make the current smaller and see if that makes the battery not die so quickly. So I'm just going to change them all to like 1 times 10 to the -1. Okay, yeah, so now the battery is not dying so quickly, so let's make the time step larger. Or not the time step, the total time. Yeah, so this is a pretty reasonable voltage curve. We could also plot our concentrations at this edge and compare what they look like in the positive and negative. So I'm going to plot yeah, so these are the concentrations of vanadium oxide and vanadium dioxide in the positive half cell. So you can see they increase and decrease at the same rate because they're in the same part of the battery, so they're directly related, their reaction. Yeah, I mean that's pretty much it for this. Then you could also add in effects of like flow effects, like convective stuff, or like how, since this is a flow battery, you wouldn't really have this like static concentration in your battery, so you would have a larger pool of of active material and electrolyte, and then you could track with some overall volume what is your overall amount of each of these species, and then add that concentration from the bulk of your electrolyte tank in some sort of source term into your overall concentrations, while subtracting some of your old concentrations that were already in like the battery in the electrolyte. So like trying to simulate the flow of electrolyte throughout the flow battery. Also like convective effects for diffusion and electric field stuff. And you can also look at like in the membrane itself, it doesn't totally have perfect diffusion. It's not necessarily super fast, though it probably isn't like the limiting factor in the battery. But you could look at like what's the concentration gradient in the membrane. Do people's codes work, or are they not working?
Mine's not working. I don't know what's going on. It says undefined function or variable of initial. I don't know where.
What's the error on?
My line 52. Let me see. Scroll down.
Is it somewhere in like your this function?
Wait, what the hell? Scroll down. It's in the second one. Okay. Initial. I just spelled initial wrong. I think it's alright. It says 54.
So work after you fix that.
Let me see. Tradition.
Maya, can you go back up?
Yeah. To where?
All the way to the top. Yeah. Thank you.
No problem. Does anyone have any questions or anything? Sort of went through it kind of fast.
Not really. Let me see. I'm trying to get it to work though. Concentration. Concentration. My E isn't working.
This part?
Yeah.
What-
So the
what
matrix
error does it give
dimensions.
you?
The matrix
Yeah,
dimension
same.
doesn't agree.
Hmm.
I put the periods. Let me see.
If the dimensions don't agree.
Yeah.
In this function, did you define it as nt and x?
Concentrations. Where's that?
This is
Oh.
the solver function.
NX and NT, yeah.
Hmm.
Yeah, I have it.
Does it say specifically where in the line the error is?
It just shows up the whole function or the whole equation. Let me see. Let me look for it.
The error usually gives you like a column.
This one didn't. Let's see. Line. It just says line 13 on mine.
I mean, do you want to share your screen?
First. The host disabled it.
Screen sharing is disabled?
Yeah. You got it.
Let me see if I can. I don't know if you want to change that. Wait, try again. It still doesn't let you?
Oh, yeah, so it doesn't let me.
Oh, I see. Try now. Whoops, Ronaldo's waiting.
There.
You scroll to the right.
Maya,
Yeah.
I think Ronaldo is trying to get in. He's been trying to get in.
Sorry. I wasn't looking at the wait list. I hope you weren't waiting that long.
Oh, but who's that? I'm just kidding.
Poor guy.
Diet concentration. Wait, what? Oh, no.
It might have something to do with your concentrations, H.
Concentration. This one?
Yeah, what if you take that one out, see if it works? You have to take out the multiplication too. Yeah, and then run it.
Oh, it ran. Yeah, it worked. Without it.
Yeah, so there's something that's
go
in
down to
concentration H.
Go down to the function for your concentration H. Try switching the dimensions to like n. Try doing like nt comma 1 instead of 1 comma nt in line 53.
Line 53.
I don't know. Will that change it?
NT comma 1.
I mean, I have it the other way and it's working for me, but
Let me see what it looks
maybe what you're sure you're setting it to the same like time and dt in your concentration H, because if those are different, then it'll be a different size.
Well, what is this?
No, yeah, it's different. Like you have 30 seconds in your concentration H and 60 in your other ones.
Oh, you tell me this now? Okay. Line 21.
You don't have that variable anymore.
Where is it?
Oh, it's just they're called like concentrations underscore something now, not just concentrations.
What do you have it on?
I mean, it doesn't really matter.
It could be anyone?
Yeah, you're just plotting there. Or it should be like, yeah, one of your. You can plot any of them really, just not the concentrations H, since it's not like a. We didn't calculate it for all of space.
Is that what you said?
Yeah, pretty much.
First try. Did yours work? Oh, Kelly?
Yeah, did you get it to work?
No, I don't have the same graph as you. So I don't know where I went wrong.
Like it's slightly different, or it's like wildly incorrect?
It's different.
Were the concentrations like similar?
Yeah, I think I have the same one as you. Can I see your code again?
Yeah, sure. Which part? This part?
The beginning part. Yeah. Let me see.